So the first one I have, and for all of these really, we have equations, and we're trying to figure out how do I get these two equations, these two values to actually be equal to each other. So in the first problem, we're trying to see what value of x would make the equation true. And as we know, we learned yesterday, there's a couple of rules that allow us to turn radicals into exponents, and then the other way around. You can turn exponents into radicals. So actually, let's just review that really quickly. I'll do that over here on the right-hand side. So if I have a number, I'll just call it a. If I have a number to the power of, let's do 1/3. How can I rewrite that using a radical?
Put a inside the radical and then put one inside, but you don't have to put one because it doesn't, like, it's still the same without the one. And then you put 3 outside.
And the 3 sits out here. Exactly. So, and like Ajira said, that 1 that's on the inside, we don't really need to write it because anything to the power of 1 will just stay the same. So I can erase it. So that would be if it was 1/3. Let's do another example. What if I had a to the power of 3/5?
A inside the radical, then 3 inside as well, and then 5 outside.
Good. The 5 can sit out here, and the 3 can go inside. And you can do this both ways. So now let me do 1/3 example. What if I started with the square root of a to the power of 3? Now, how would I go about turning that into an exponent?
A by the power of 3/2.
And where did that 2 come from, Ajira?
Since the radical basically is square root and then a square equals 2.
Good. So whenever there is no number on the outside, remember there's always an invisible 2 sitting out there. You don't see it, but it's there. And so the 2 goes into the exponent's denominator. That's my 2. And the 3 belongs in the numerator. So always when you have these types of problems like the ones in this spell ringer, you always want to start off by switching it up. So if something is in a radical, turn it into an exponent. And then what that's going to help you do is then when everything is exponents, whenever you have exponents, you can use the rules of exponents to simplify things. So I'm going to start by doing that in example number 1. On the left side, notice I have a radical and I have an exponent. Okay, so I have radical on the inside of the parentheses. I have an exponent on the outside of the parentheses. We want to turn this radical into an exponent because then we will be able to simplify it a little bit better. So I have the p over q. We're going to leave that just the way it is. So I still have p over q. But now, instead of the fourth root, technically that's called the quartic root of p over q, this thing is going to now have an exponent. So remember, the 4 was sitting outside. That's the one that's sitting on the ledge. So does that become the numerator or the denominator?
Denominator.
It's the denominator. And what goes up into the numerator then?
1.
1, exactly. Because is there an exponent on the inside? Do we see an exponent inside?
No.
No, right? So since there's no exponent, you can think about it like there's an invisible 1 on the inside. So the 1 goes into the numerator, the 4 belongs in the denominator. But then I have this other exponent. So I'm going to add even more parentheses and bring that exponent down. Okay, so let's take a look at what's happening here. So what we did is we turned the radical, we turned it into an exponent. Now, what do I have? I have 2 exponents. I have 1/4 and then I have 4/3. And that's actually much, much better for us because what can we do now between these two exponents?
Distribute.
Distribute. Exactly. When you have an exponent on the inside of the parentheses and then an exponent on the outside of the parentheses, you can distribute, you can multiply those two numbers. So I'm doing 1/4 times 4 over 3. What is 1/4 times 4 over 3?
4 times 3 is 12. Well, we need to have it as the same denominator, right?
Nope. Remember, when you multiply fractions, can anyone remind me, how do you multiply two fractions together?
You multiply across.
Straight across, yeah. So I'm doing 4 times 1 and then 3 times 4.
Okay. 12. 4 times 3 is 12. Then 1 times 4 is 4.
Perfect. So 4 over 12. Well, look at that. We're really close to figuring it out because now these two sides of my equation, they match much more closely. So I know that x is going to be matching with 4 over 12, but I can simplify 4 over 12, can't I?
Yes.
Yeah, how do I simplify that?
Divide by 4.
Divide both top and bottom by 4, so I have 1/3.
1/3.
That's answer choice C. So, okay, it's a complicated problem because they make it look hard, but at the end of the day, all we're still doing these rules right here that I wrote down at the beginning. We're switching things back and forth. If they show you it as an exponent, turn it into a radical and see if that helps. If they show you it as a radical, turn it into an exponent and see if that helps. Because sometimes it's easier to do the math if it's an exponent. Sometimes it's easier to do the math if it's a radical. So we're going to get real comfortable going back and forth between fractional exponents and radicals. How are we feeling about number 1? I know it's more complicated, so any questions on how I got any of those numbers? Okay. Now, number 2 is kind of very similar. Take a look at number 2. It says determine whether each equation is true or false. In the case that you find a false, explain why. So basically, we're trying to see if the left side is going to match the right side. And what we're going to need to do is kind of use those rules of turning things from radicals to exponents or exponents back to radicals to see if we can get a match. So we're trying to see if we can get a match on the left side versus the right side. So I'm going to erase these rules. And let me just start with number 1 as an example. So I have the square root of 32 equals 2 to the power of 5 over 2. So one thing that I would start off with is I would say, okay, on one side I have a radical, on the other side I have an exponent. I want those two to match. So I'm going to start off by turning this one, turn it into a radical. Because then when I have radicals on both sides, I can see if they match. So I'm gonna keep the square root of 32 the same. And now let's turn this into a radical. So how do I do that? What goes inside? What goes outside?
Well, you don't have to put the 2 outside, right? Or do you have?
You're completely right. You don't really have to. I'll put it there for now, but I'll take it away in a little bit. So 2 is on the outside, and then the
inside.
5 is inside. Okay. So that then I can see if I can take it a step further, because right now, so far, a couple of things match. Both of them have the square root. So that's really good. So I know that that part matches. But then on the inside, I see 2 to the power of 5. You can do 2 to the power of 5, right? That's not too bad. We're going to do 2 times 2 times 2 times 2 times 2. What does that give me?
Well, 2 times, 4 is 16, right?
Mm-hmm.
And then 16 times 2 again, it's...
What's 16 times 2?
32.
It's 32. So 2 to the power of 5 is, in fact, 32. So we have a match. So in this case, we do have a match. This is true. And so that's what we're going to basically do in each problem. We're going to see, okay, can I somehow turn this into the other? See if we can manipulate it by switching it into a radical or an exponent in order to get those two sides of the equation to match with each other. Any questions on this first one? We'll go ahead and we're going to do all of these together. I definitely want to make sure I'm explaining it. So any questions on the first one? Okay, so let's try the second one. Second one, I have 16 to the power of 3 over 8, and then 8 squared. And we're trying to see if these two are equal to each other. So can anybody, there's no wrong answer. Can anybody give me one way to maybe try to start this off?
Turn the exponent into an radical.
Okay, so let's go ahead and turn that exponent into a radical. So 16 stays on the inside. And who goes outside?
8.
8 goes on the outside. And on the inside?
3.
3. And then on this side of things, what goes on the inside?
1.
Think again. Remember, the exponent is 2, but as a fraction, that would be 2 over 1.
Oh.
The 1 goes on the balcony.
Yeah, so the 1 goes on the balcony.
And the 2 goes inside.
Now, is that a thing, though? Can you have a 1 in the balcony?
No.
No, that's actually not a thing. Remember when there is no number there, what number is it?
2.
It's a 2, not a 1. So that's actually not a thing. So that's very interesting. We can't really turn that into a radical. So I'm just gonna leave this as 8 to the power of 2. But let's see what's going on over here on the left side. So 16 to the power of 3. Does that seem like something I want to do without a calculator?
No.
No. Calculator's out. Let's try this out. Let's see if we can get a match. So 16 to the power of 3, that's 16 times 16 times 16. What do you get?
4,096.
4,096. Now, what is 8 to the power of 2? Because that we can do. What's 8 squared?
2.
8 squared. So 8 times 8.
64.
64. So now we're trying to see, okay, does the 8th root of 4,096 equal 64? Now, here's where we're going to talk about a new button on the calculator. Let me see if I can actually share my screen on the, oh, I have a calculator on the iPad. Fancy, fancy. Hold on. Okay. Where's the calculator? Do you guys see it? There should be one.
There should be one.
Miss, I saw your cat.
Yeah. Where is the calculator? Maybe I don't have one on here.
Yeah, I think you have to.
I think you have to download it. I don't think tablets come with it.
Yeah. Oh, that's too bad. Okay. But you know what? There's always
Online.
The Safari one.
Yeah. Okay. I was making cookies yesterday, so that's my search history. Okay, so on here, let me see if there is one. If they have the button I'm looking for.
They have square root, but they don't have cube.
Yeah. Okay, so this one might not be the most useful
Maybe you
calculator.
can go to Math Away.
Well, you know what? There's actually one of my favorite calculator. I have this app. Do you guys see the green one that says Desmos?
Oh yes.
That is
Yes.
an amazing app, you guys. This is something I highly recommend you download because it's really good for graphing. So we're not really doing a lot of graphing this week, but we're going to start graphing next week, and it has a good calculator too. So see this calculator. Okay. Let me see if this one works. I have this. Can I put a different number in there? I don't think I can. This is what it's called when Miss Lopez does not prepare for her class. Okay, I don't know if it's going to be possible, but on the iPhone there is a button. So that's why I wish I could figure out this. Okay, well, there you see this. So the square root of 4,096 equals 64. The square root, but hold up, where is it? What do we have here?
8 by 64.
The eighth, this number out here is an 8. So if I know that the square root of 4,096 equals 64, then does the eighth root of 4,096 equal 64?
No.
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 So that does not work. So this one's false. Now, next time, maybe I'll download that calculator app because it is very useful to show you guys that button. If you happen to have an iPhone and you look at your calculator, you'll see the square root, you'll see the cube root, and then the next one has a little y. I don't know if you'll be able to see it. Kind of, not really. Okay, kind of. It's hard to tell, but there's a square root, a cube root, and then a little y, and that little y means that you can put whatever number you want on the outside.
Really?
Yeah.
I
So
never
I think what you do is like, let me see.
Oh, if you do 8 by the power of by the square root of 4,800, 096, it's like all decimals, 1.00.
Yeah, I got it too. So it does not give you the right answer. So long story short, this one is false. Let's try the next one. All right, 4 to the power of 1/2 equals the fourth root of 64. So there's two ways we could do this. Should I turn the left side into a radical or the right side into an exponent?
The wait, which one is your left and which one is your right?
So should I turn 4 to the power of 1/2 into a radical so that they're both radicals? Or should I turn the fourth root of 64 into an exponent so that they're both exponents?
Radical?
I think you should turn them into an. Nah.
Let's do the radical. That sounds good.
If you turn it into an exponent, it won't be the same because 64 by the power of 1/4.
Right. It won't be quite the same. So, all right, 4 to the power of 1/2 is the same as what number goes outside?
2.
2 goes outside.
2 goes outside. So this is the square root of 4. And then the fourth root of 64. Okay. Well, what is the square root of 4?
Isn't it 2?
Yeah, let's do the square root of 4 is 2. We know that. And then the fourth root of 64. Is that a number we know?
Oh.
It's not, is it? It's kind of a little harder to get that one. But remember, when you take the root of something, it's the opposite of an exponent. So for example, how did I know that this was 2? Well, that's because 2 to the second power is 4. So if I'm looking for a number over here, if I'm trying to figure out what is the fourth root of 64, I'm just looking for a number that if I take it to the fourth power, whatever that number is, it should give me 64. So is there a number that when you multiply it by itself 4 times gives you 64? I'm seeing somebody is suggesting the number 4. Okay, let's try it out. So
No.
4 times 4 is 16. Times 4, 16 times 4
64.
is 64. So 4 to the power of 3 is 64, not to the power of 4. So it's not 4. You can try 2. 2, 4, 8, 16.
16.
2 to the power of 4 is 16, not 64. 3, 3, 9, 27. 27 times 3 is 81.
That means it's gonna be lower, so it's gonna be a decimal.
So it's going to be a decimal. So are these going to match?
No.
They are not going to match because it's not 2. We've determined that it's not 2. So these do not match. This one is also false. Now, another way you could have done this, and let me just go through it real quick, is the other way. Remember, we could have turned the 64 into an exponent. So if this is 4 to the power of 1/2, this would be 64 to the power of 1/4. But we know that 64 is the same as 4 to the power of 3, right? 4 to the power of 3 is 64. So I'm just gonna change that 64 so that it matches. So now this is 4 to the power of 3 to the power of 1/4. So does anyone need me to explain what I just did there? All I did was I turned 64 into 4 to the power of 3, just because that's what it is. They match.
It?
And then what should I do between those two exponents?
Distribute.
Distribute and multiply. So what's 3 times 1/4?
3/4.
3/4. Does what 4 to the power of 1/2 match 4 to the power of 3/4?
No.
No, these don't match. So that's the other way to that you could have done that. To just prove that they don't match at all. Okay, 2 more. So 2 to the power 8. And then the cube root of 16 to the power of 6. Okay. What do y'all think? Let's maybe turn things into exponents this time instead of radicals. So how do I convert that into an exponent?
We have to find the cube root of 16. No, wait. Yes.
So I'm not going to evaluate it yet. I'm just going to turn it into an exponent. So converting it.
Not bad. So 16 is going to be outside. No, not outside, but like for the base. 3 will be the denominator, and 6 will be the numerator.
Okay, great. Can I simplify that?
Yes.
Yeah. So what do I get?
2.
16 to the power of 2. Right? Because 6 divided by 3 gives me 2. Okay, well these are easier numbers to work with, right? I can do the math. 2 to the power of 8. What do I get? 2 to the power of 8. Two times 2
256.
256, yeah. 256. And then what about 16 squared?
256.
Also 256. We got a match. So do you guys notice how sometimes like this kind of looks a little more complicated, but when you turn it into an exponent, you can clearly see that you can simplify it. And then we ended up with something that was actually pretty easy, not too bad at all. Now, one more thing. just kind of want to show you this again. 2 to the power of what is 16?
2 to the power of 4.
2 to the power of 4 is 16, right? So I can turn that 16 into 2 to the power of 4. And then to the power of 2, because I'm bringing down that exponent. Now, the reason I'm doing that is so that the bases can match, and when the bases match, you can compare them. So now I can multiply 2 times 4 gives me 8, and that's just another way to show that these match. So you can either evaluate it and actually do, okay, 2 to the power of 8, 2, 4, 8, 16, 32. You can do that, or like I did just now, you can get the bases to match, and then that way you can compare to see if they are equal. 2 ways to do that. Questions on these so far on this one? All right, cool. This is move on to that last one. So again, we have something that looks a little more challenging because they wrote it one way, but when we write it the other way, it might make it a little more simple. So on the left side, I have the square root of 64 to the power of 1/3. Can I do the square root of 64? Do we know that?
Square root of 6.
Yes, it's going to be 8.
It's going to be 8, yeah. Square root of 64 is just 8. So I have 8 to the power of 1/3, and then 8 to the power of 1/6. Do those match?
No.
No, they have different exponents. They are not equal to each other. So see how that one, like, they make it look hard. They make this look confusing and difficult, but like, you know what the square root of 64 is. So it's a little bit easier once you kind of simplify it down a little bit. So that's false. So these problems, like, I'm going to keep giving you guys these types of problems for bell ringers because they're complicated, but I want you guys to be okay with that. I want you guys to understand that like it is complicated, but you have the skills and the knowledge to work with it, and it's kind of like a puzzle. Like, you can try one thing, see if it works. If that doesn't work, try a different thing. And there are many ways to get an answer out of it. There's more than one possibility to try to see, who's calling me, to try to see if they match. So, always try your best. Like, I know that it looks complicated, but always try your best to work through those types of problems using the rules, following the rules, and then just seeing it where it leads you. And you're totally allowed to make mistakes and start over and try it again. But like I said, I'll keep giving you guys problems like these as our bell ringers so that we can do it together. Now, today we're moving on to a slightly different topic. It's all related, but actually what I think is you guys might find today's class a little bit easier. It's a little different than what we've been doing, but I think you'll be happy with it. It's a little bit easier. We're going to be talking about rational and irrational numbers. And I've kind of talked about those two words this week, but I haven't really explained what they mean yet. So that's what we're going to be working on today. So what is a rational number? I want you guys to go ahead and write down this definition in your notebooks, as well as all of these examples. There's a lot of them. But go ahead and start writing these all down so that we can get a really good sense of what a rational number actually is. I'll give you guys a couple of minutes to do that. All righty. So continue writing because I will continue to work on this page. I'm not going anywhere, but a rational number is any number that can be written as a fraction. That's all a rational number is. So let's go ahead and look through these examples and let's figure out if the number is rational or not. And since you're trying to figure out if it's rational, you want to see if you can write it as a fraction. If you can, then it is. If you cannot, then you're out of luck. So let's start with the number 7. Can you write that as a fraction?
Yes.
Yeah, how do I write the number 7 as a fraction?
7/1.
That's 7/1. So this is rational. I'm just going to put an R. It is rational. How about 0.25?
I believe
1/4.
1/4.
Yeah, 0.25, that is 1/4. So therefore, this is a rational number. That's good. 3/4, that's already a fraction. Don't have to do any more work. That's a rational number. 1.75.
7/4.
1.
7/4. So yeah, this is the same as 1 and
3/4.
3/4, which you can rewrite as an improper fraction. How do we write something as an improper fraction?
we divide and multiply, right?
Close. Close, close.
You multiply and add it.
Multiply and then add. So 4 times 1, multiply that. 4 times 1 is 4. Then you add the top number. So 4 times 1 is 4, and then 4 plus 3 is 7. So that's how we got 7/4. So that's good. It is rational. 0.18181818181818 repeated.
Not rational.
Is it possible to write this one as a fraction?
No.
Try different things into your calculator. Try different things. Try 1/3, 2/9, 1/11. Just try different things. See if anything looks similar or close to that. I just dropped my pen. I'll be right back. Okay. Anyone found it yet?
I did.
What is it?
Mm, wait. 90,909 over 500,000. I think it looked like. I'm not. I
Oh,
don't
you
know.
were close. That one has a 0 in front of it. It's actually a much easier number than that. It's two numbers that are less than 12.
2/11.
I'm trying to
Two.
simplify the number.
What did you get? 2/11
or 10.
11. Yeah. Go ahead and plug that in your calculator. 2 divided by 11. 2/11.
Aha.
Ah, see, there it is. Rational. And we'll talk about that in just a moment. But let's keep going. Square root of 25.
5.
Is 5,
5,
which is the same as 5/1. That's definitely rational. How about square root of 16?
4,
It's 4. Rational. -3.
what?
By -3. No. That don't make no sense. 1. No, -1/3.
Well, that's -1/3.
Oh, 3, -3 over 1.
-3/1. That is rational. There's nothing against negative numbers here. Doesn't say anything against negatives, so we're good. How about 0.6666666666666? Remember that bar on top of that 6 is the repetition bar.
Is it 2 by 3? But it's not 66666 all the way. It's 66666 by 7.
So that's something very important. So depending on the calculator that you have, if you have an iPhone or an Android, I think as well, what it's going to do is it's going to show everything up to the very last spot on the screen. And then once it's out of room, it just rounds up. So what happens if you turn, okay, if you're getting, oh my goodness, you can't see it at all. Okay, if you're getting this 0.6666667 and you turn the screen, what happens?
Turn the screen?
Mm-hmm. So I just turned mine, I flipped it.
Oh, yes, it's 66666, but it ends at 7.
Right. So what an iPhone does, and some calculators actually do this as well, is it rounds up at the very last number. But what it actually should do, what it actually means is that this is a repeating decimal that goes on forever. It's never going to stop. It's just going to keep going 66666 forever. So yeah, 2/3 is the correct fraction for that one. 2/3. All right, and then finally 0.4.
4/10.
Yeah, 4/10, which simplifies to what?
2/5.
2/5. Rational. Okay, awesome. So let's kind of talk about what we noticed. So what types of numbers can be rational numbers? So it's not just fractions, but what other types of numbers can fit into that category?
Integers,
Mhm.
world numbers.
So integers, so positive and negative whole numbers.
Decimals.
Decimals, but what type of decimals specifically? What's going on here? So let me start writing these down. So we have integers. And there's two types of decimals that come up on this screen. There's terminating decimals. Can anyone tell me what does terminating mean?
Delete, destroy.
Actually, no. There's another definition for that word. Oops, I wrote definition. When you terminate something.
I don't think none of us know.
Yeah.
So you guys probably know it in the context of like destruction. So terminator, right? Like you destroy things. But really terminate just means to end. Like on the basic, it just means it ends. So if something if I terminate my lease, my contract, I'm just ending my lease or my contract. So it's just terminating just means to end. So which decimals here stop?
Stop.
0.4.
0.4, that one just stops at the 4. What else?
0.25.
0.25.
1.7.
1.75.
And 1.75. So those are terminating decimals. But on the other hand, you have repeating decimals. Which ones are those?
The infinite ones, so 0.6, 0.18.
0.6 and 0.18181818, right? So repeating decimals, they don't ever stop. They keep going forever. However, something important is that they follow a pattern. So in this case, the repeating pattern for example E is 1/8 because that repeats forever. The repeating pattern for example I is 6 because it's just going to repeat forever. So these three numbers fall into that category. So we've got integers, terminating decimals, and repeating decimals. Any questions on what makes something rational? Okay, so we've got rational numbers, but on the other hand, we've got irrational numbers. So can I get a volunteer to read what is an irrational number?
Mm.
You already have 25.
A irrational number is any number that cannot be written as fraction. Irrational number has an infinite non-repeating decimal.
Awesome, perfect. So go ahead and write down that definition as well as the examples in here. Alrighty, so we've established that rational numbers, you can write them as a fraction, right? So irrational numbers have to be the opposite of that. You cannot write them as a fraction. So let's kind of start looking at these examples and then we'll talk about which ones are rational and which ones are irrational. Starting with A. What's A? Square root.
7.
That's 7, right? Square root of 49 is 7, which we know that that's 7 over 1, so A is definitely rational. How about B?
Rational, we
5.
already did that.
Yeah, we already talked about this one. This one's 5, or 5 over 1. That's rational. Pi. What's pi?
That's
3.14.
3.14.
Does pi end at the 14 or does it keep going?
it keeps going.
Keep going.
Different numbers.
Going, yeah. Does it ever end?
No,
No.
Does it follow a pattern?
no.
No. So
it's
pi
irrational?
is irrational, yeah, because this is 3.141592653, and it keeps going. And yes, I did memorize that. So there is no pattern. It does not repeat. However, it is infinite. And so if you read the bullet point one more time, the bullet point says irrational numbers have infinite, non-repeating decimals. And pi fits that category. It is infinite and it does not have a pattern. So it is irrational. We already talked about 0.6 repeated. What's the difference between C versus D?
D has the same number every. It's the same number every repeating time.
Right. So even though it is infinite, it has a pattern. And so since it has a pattern, that makes it rational. Square root of 7. The square root of 7. What's up with that one?
It is irrational because you can't do the square root of 7.
Right. You can't really take the square root of 7. And if you try, if you go on your calculator and do so, what do you get?
2.64, 57, 51, blah, blah, blah.
Blah, blah, blah. Right. That number is repeating. It's non-repeating and it continues on forever. Now, again, your phone is going to cut it off at a certain point because there's just no more room on the screen. But in reality, what's going on is this is continuing on and on forever. And that makes it irrational. How about the square root of 12?
Just a decimal.
It's a decimal. Does it follow any patterns?
No.
Does it end?
Yes. Wait, no.
It ends on your screen, right? It ends on your screen, but if you, and that's something that like, it's kind of hard to tell because sometimes your screen might show you one thing, but one thing you can do is try plugging it into the computer calculator or the Google calculator or Desmos if you download that app, and you'll see that it actually does keep going. It keeps going on and on and on. This is 3.464101 ... It keeps going. So that is also irrational. How about G, 0.444 ...
Rational.
Yeah, we've already established that repeating decimals are rational. Does anyone know what that fraction is? I'm going to show you guys a cool trick, and you can actually check it on your calculator. Okay, 1/9 is 0.1111 repeated. 2/9, 0.2222 repeated. 3/9, 0.3333 repeated. So what's this one?
4/9.
Yeah, it's 4/9. So rational. And then the last one, the square root of 125.
It's irrational.
Irrational. This gives me this gives me 11.1803398 ... Irrational. So let's kind of talk about the patterns we're noticing. What types of numbers end up being irrational?
And numbers that don't have a perfect square.
You got it. Exactly. So I'm going to add a little bullet point here. We're going to add this to our definition. Irrational numbers, any number so that is the square root of a non-perfect square. So the square root of a non-perfect square. If it's a perfect square, it gives you a whole number, you're good to go. But any other number than that, a non-perfect square, will always give you an irrational number, irrational. And so any of those count, and then pi is another one to just always remember. Pi is also irrational. Any questions on what makes something rational, what makes something irrational, or anything like that?
I have a question, but it's like not related to the irrational.
That's okay. You can still ask.
Well, we use pi in high school, or is pi just there for 6 and 7?
You'll use it in geometry, and you'll use it if you go on to do calculus. So yes, it'll come back.
No.
Sorry.
Circular, radius.
Yeah.
I forgot the other ones, but I'm gonna have to remember it again.
You will. You will. But once you pass algebra, you'll see pi is the least of your worries. Alrighty, y'all. So we've established what is rational, and we've established what makes something irrational. Now we're going to talk about how to do operations. We're just going to talk about addition and multiplication today. That's all. And we're also going to notice some patterns with this. So I've set up a few problems. We'll go through them one by one, so you don't need to write all of them down right away. But what we're going to be doing is we're going to see what happens when you add rational plus rational, irrational plus irrational, and then rational plus irrational if you mix it up. So with the first set of examples, we're trying to see what happens when you try to add a rational number with another rational number. We'll see what happens. So I put up a few examples because examples always help us to kind of see what the pattern is. Let's take a look at A. 3/4, that's a rational number. 1/3 is a rational number. Let's add them up and see what happens. How do I add these two fractions together?
Butterfly or
Mm,
crossover or straight across.
no, we can't go straight across because we need something to match first. What has to match?
Oh, the denominator.
The denominators have to match. So what can I turn both of these fractions, we're going to have to turn them into something else so that they match. What would
12.
be good? I was just going to say, what would be my common denominator? It would be 12. So 3/4, what is that over 12?
Well, we're dividing 3/4 by 3, and then we're dividing, not dividing, I'm sorry, multiplying 1/3 by 4. So it will all be 12, except for 1/3 because 1 times 4 equals 4.
So 1/3 becomes 4/12. And then 3/4 would be what over 12?
9.
9/12.
9. Oops, I'm sorry.
That's okay. So 9/12 plus 4/12, how many 12ths do I have?
1. Wait,
9
how many
plus
12s?
We're adding those 12ths up. So 9/12 plus 4/12.
13.
Over 12?
Yeah, 13/12. 13/12. Is that a rational or irrational?
Rational.
That is rational. So we end up with a rational answer. Rational number plus a rational number gives me a rational answer. But let's check to see if that always happens or if maybe not. So now I got 7 plus 13/2. Well, again, I have two numbers that they need to match with the same denominator. So 7/1 becomes what?
2.
14 over 2?
14/2.
I'm sorry.
That's okay. No, this is something that we definitely should be practicing. So that's good.
I always do that. Like I don't check for the other number.
Yeah, remember when you're trying to get the denominators to match, you're going to have to change the numerator and the denominator. So 7/1 is the same as 14/2. And now I'm adding 14 plus 13.
27.
27.
Yeah, 27/2. I have a rational number. So far 2 for 2. We're good. How about this last one? 1/5 plus 4/5. Do I need to change anything?
No.
No.
Nope. What does this give me?
5/5 equals 1.
5/5, which is 1. Rational. So 3 for 3, a rational number plus a rational number will give me a rational answer. And that is a true fact. Anytime you have two rational numbers, no matter what they are, you're still going to get a rational answer when you add them up together. Any questions on that? Cool. Well, now let's see what happens when you add a irrational number with another irrational number. So starting with A, this is a little weird. The square root of 3 plus the square root of 3. Does anyone know what that would mean? What that would give me?
It's irrational?
Yeah, that's still going to be irrational because let's think about it. This is a non-repeating infinite decimal. Then you have another non-repeating infinite decimal. When you add them together, you're still going to have a non-repeating infinite decimal. Now, what we can do we can kind of think about this like combining like terms. I have one square root of 3 over here. I have another square root of 3 over there. How many do I have in total?
2.
I have 2 in total. So this is 2 times the square root of 3. But I can't do much more than that. I can't really simplify that any further. I can't get rid of the radical. I can't take the square root of 3 because I know that that's going to give me an irrational number. So at the end of the day, that's all I can do. And I know that this is still going to be irrational. Now, let's see if that tracks. Let's see if that happens in the next example. The square root of 7 plus the negative square root of 7. If I'm adding a negative, what is that the same as?
Adding. Wait, no, subtracting.
Subtracting, exactly. So if I'm adding 7, the square root of 7 plus negative square root of 7, I can rewrite this as the square root of 7 minus the square root of 7. Well, what happens here? If I have the square root of 7 and then I take it away, what am I left with?
0.
0. Now let's think about this. Is 0 rational or irrational?
Irrational. Wait. 0 is not a whole. Is 0 a whole number?
Good question. Good question. So 0 is one of those weird numbers, right? Because it's kind of like not, it's like the absence of a number, if that makes sense. But can you write 0 as a fraction? That's always what you're going to think about. Can you write it as a fraction?
0 over 1?
Yeah, exactly. Because what is 0 over 1?
0.
It's still 0. I wrote it as a fraction. So 0 is a rational number. We do count that as a rational number. So in this case, my answer is 0, which means my answer is rational. It's kind of a special case. It is rational. What about C though? The square root of 6 plus the square root of 7.
They're not like terms, so we can't. Well,
Yeah, you're right. Can't combine them. They're not like terms. They are both irrational. So if I have an infinite repeating, non-repeating decimal plus another infinite non-repeating decimal and I add them together, I'm still going to get an infinite non-repeating decimal. You can't actually write this any other way. I still just, the only way, the simplest way to keep this when I write it is just the square root of 6 plus the square root of 7. It's kind of like if you have x plus y, there's no other way to simplify that. You still just have x plus y. So this is also irrational. So is there a hard and fast rule for this type of addition? Irrational plus irrational?
not really.
Not really, right? Because there's that one exception. That one exception is that sometimes your answer is just going to be 0. So when that happens, if your answer ends up being 0, I can't write a rule. I can't say that this is going to work out every time because there is an exception. So an irrational number plus an irrational number, let me write this down over here, is going to be sometimes. Sometimes it ends up being rational. Most of the time it's irrational, but sometimes it's rational. Okay, now let's look at these last ones. This time I'm mixing it up. I'm doing one irrational number and one rational number. So an R and an I. 3 plus the square root of 3. Are those like terms?
Yes.
They are?
Well, well, no, actually no, because the 3 doesn't have a square root.
Right. One has a square root, the other does not. They're not like terms. They are not. So we can't combine them. I can't just magically slip underneath that radical and mix them up together. I can't do that. Because when you're adding two numbers, you can't like, you know how sometimes you can kind of bring them together? That's usually with multiplication. With addition, I can't mix those two numbers together. I have 3 over here and I have the square root of 3 over there. Well, if I just add 3 to the square root of 3, in fact, what is the square root of 3? If I plug that into my calculator, the square root of 3, so the square root of 3 is, let me just add 3 plus 1.732050 dot dot dot. If I add 3 to that, well, then I just have 4.732050 dot dot dot. So it's still going to be
Irrational.
irrational. How about 3/4 plus the square root of 3 over 4? I have two fractions. Do they have matching denominators?
Yes.
Yes.
They do. So I can combine them, but when I combine them, I get 3 plus the square root of 3 over 4. And like we just determined, 3 plus the square root of 3 is an irrational number. So my final answer is irrational as well. And then finally, 3 times 3 root 2 plus 11. If I add 11 to an irrational number, it's going to make it bigger, but it's still going to make it, it's going to maintain irrational. It's going to stay irrational.
Oh, this is like adding like a negative to a positive, maybe? I don't know.
Oh, like when you add a negative to a positive. Well, there is, it's kind of hard to say because there's not really a rule for adding positives and negatives because like that depends on the scenario. So it's not quite the same thing. But this actually, we can conclude that an irrational number plus an irrational number is an irrational number. Oh wait, sorry, I mixed this up. A rational number plus, so when you mix them up, rational plus irrational, it's always going to stay irrational. Okay, so do I have any questions on this? We're going to summarize it in just a second. So it kind of looks a little messy, but I am going to summarize it. But do I have any questions so far? Okay. So let me start off by, actually, let me read what I wrote here. So it says, rational numbers are closed under addition. So what that means, this is kind of a new word, closure, closed. When something is closed, what it means is that when you start off with one thing and you add it together, you end up with the same type of thing. So let me go back. Let me explain that. So we already established that rational plus rational equals rational. You start off with two rational numbers, you end up with a rational number. What that means is that it's closed under multiplication. That's just a kind of a weird vocabulary word that you might see every once in a while, so it's important to know what it means. When something is closed, it just means that you start off with one thing and you end up with the same thing. A rational number plus a rational number stays rational. Are irrational numbers closed under addition?
No.
No, right? Because irrational plus irrational sometimes gives you irrational, but we already noticed that there is an exception. So since there's an exception, it's not closed under addition. So what we're going to do is we're going to write down the following rules for addition with rational and irrational numbers, and we're just going to make this little chart. So
Am I
find
just seeing that smiley face?
what? I don't know who made that, but it's cute. Okay, we're going to make this little chart. So rational, irrational, rational, irrational. And this chart is an addition chart. So this is what happens when you add. Make a little plus sign. When you add rational numbers with irrational numbers. So what happens here when you have rational plus rational?
Rational.
Is rational. It's closed. And it's always rational. What did we determine with irrational? So these two boxes right here, irrational and rational. When you mix
Still
them together.
irrational.
Good. In this case, it's always irrational. So in other words, it's never rational. When you mix them together, it's never going to be rational. But what happens when you have irrational and irrational? Right here. What did we determine? Most of the time, it's going to be what?
Irrational.
Irrational, but every so often you might end up with 0. That's my exception. So sometimes, every so often, sometimes it's rational. So go ahead and write these 4 distinctions down, make that little chart. And this is going to be a very, very helpful way to organize and to remember which scenario gives you which result. So go ahead and just write that down. Any questions on this slide here? Awesome, awesome. Does anybody need another minute to write it down? Okay, 30 more seconds. Alrighty. So we've talked about addition, what happens when you add rational and irrational numbers. Now let's do a couple of examples. All we want to know is I want to know which of the following are rational. So let's talk about it together. Square root of 25 plus the square root of 9. What type of numbers are these?
Rational.
Yeah, they're both rational, right? Because I have, this is 5, this is 3, 5 plus 3 is 8. This rational plus irrational is going to give me rational. Okay, B. I've got, what do I have there? I have pi. That's my pi. What did I say about pi? What type of number is it?
Irrational.
Irrational.
Good, irrational. Now in this case, am I going to get 0? Do I end up canceling anything out, or is it going to be just another irrational number?
Irrational.
Yeah, because remember,
Irrational.
always look for if you might get 0, and you only get 0 if you add and then subtract the same value. So in this case, we're not doing that. This is irrational plus irrational, and it's going to give me irrational. So this is not rational. How about C? What type of numbers do I have there?
Irrational.
So I have an irrational number, and I have a
Rational.
rational. And I know that that's always going to be what?
Irrational.
Irrational. So that's out. How about D? What do I have there?
Irrational plus
Irrational plus rational.
Good, which always gives me
Irrational.
good job. Okay. Here's an interesting one. The square root of 45 over the square root of 5. We haven't talked about division yet, have we? Because this is technically dividing. So for this one, let me actually just rewrite one. Let me rewrite it, see if it makes it a little bit easier to understand. 45 is the same as, let me think, hold on. 45 is 5 times 9, right? 9 times 5. So I have the square root of 9 times the square root of 5. So I'm simplifying this radical. I'm simplifying it. I know that, what is the square root of 9?
3.
It's 3. So this is 3 root 5 over the square root of 5. I'm just bringing this 5 right along. Well, what happens here with the square root of 5 on the top and on the bottom?
They cancel out.
They cancel out. And I'm left with
3.
just 3.
So rational.
So rational, yeah. This one, don't worry about that. We haven't gone over this. We'll do that in just a second. But that does end up being rational. And then x plus y, where x and y are irrational numbers. So this is, oops, irrational. Irrational plus irrational. Do we know for sure?
No.
We don't know. It might end up being 0. It might end up being rational in the end, but we don't know for sure, so I can't circle it because I don't know for sure. So that one doesn't count either. All right, so any final questions on adding, the patterns between adding with irrationals and rationals? Awesome. Okay, well now let's talk about multiplication. I have almost the same numbers here, pretty much the same numbers all the way around. And let's just see what happens. It might follow the same type of pattern, it might be a little bit different. How do I multiply fractions again?
Over.
Yeah, straight
Right across.
through, straight across. So 3 times 1 is
3.
3. 4 times 3,
12.
12. Can I simplify this?
Yes.
How do I simplify?
Divide by 3.
Right, so this is 1/4. Okay, so far, so good. I've got rational. 7 times 13 over 2, same thing, we're going to go straight across. 7 times 13. Seven times 13?
91.
91. So 91 over 2 is rational. 1/5 times 4/5.
Denominator.
425.
4 over 25. Because we're just multiplying straight across. Doesn't matter with multiplication, the denominators do not have to match because all you do is go straight across.
No, I was gonna say the denominator stays the same.
Oh, no, we multiply it. We multiply it because remember, multiply the top and the bottom together. So this is rational. So rational numbers are closed under multiplication as well because a rational number times a rational number gives me a rational number. Okay, what about irrational times irrational? And again, how do I know that this number is irrational? How do I know off the top of my head? How do I know that that one is irrational?
It's not a perfect square.
It's not a perfect square. Any square root other than the perfect squares is irrational. So square root of 3, irrational. Well, in this case, I'm multiplying. So when you're multiplying, you can combine those two numbers. This is the same as the square root of 3 times 3. You can bring them in together. That only works for multiplication, though. Remember, it did not work when we were doing addition. It only works with multiplication. Well, what's 3 times 3?
9.
It's 9. And do I know the square root of 9?
Yes.
Yeah, what is
3.
it? It's 3.
3.
So what do I have here?
Rational.
Rational number. Okay, how about this? The square root of 7 times the negative square root of 7. Remember what I said. We can combine underneath the radical. But I'm doing a positive times a negative, and a negative times a positive gives me a
Negative.
negative. So this is negative, but it's the negative square root of 7 times 7. What's 7 times 7?
49.
And what's the square root of 49?
7.
7.
7. So I end up with negative 7. Rational or irrational?
Rational.
Rational. That's a rational number. So, okay, interesting. So far, an irrational number times an irrational number is a rational number. Now let's see this last one. I can still combine them, so I'm going to do so. So 6 times 7. What's 6 times 7?
42.
42. Now is the square root of 42, is that a perfect square?
No.
No, right? And you can try it. You can see what happens on your calculator. If you try to take the square root of 42, you get an irrational number. So it is not a perfect square, so it's irrational. So are irrational numbers closed under multiplication?
No.
No, because sometimes you get a rational answer, sometimes you get an irrational answer. So this one, you can't close it under multiplication. It's sometimes going to be rational, sometimes going to be irrational. So there's no rule that I can write down for this one.
Oh, so if they both have like the same base number, that means it's gonna be irrational. While if they have the different base, that means it's gonna be irrational.
For the most part, yes. Though sometimes you got to be a little careful because that's not always true. Just a quick example, Ajira, to show you why. What if I tried, hold on, let me think of a good number. What if I did, hold on, I'm trying to come up with a good example. Oh, here's a good one. The square root of 4 times the square root of 9 4 times 9 is 36, and the square root of 36 is 6. So they're not the same number, right? But you still end up with a rational answer. But just remember, like if you have two irrational numbers, sometimes it's rational, sometimes it's irrational, and it really just depends. Okay, so last one, 3 times the square root of 3. Now remember, you can only combine things if both numbers have a radical symbol. In this case, can I combine 3 and then the square root of 3?
No.
No. So in this case, the only thing I can really do is write them together, 3 root 3. But that's not a rational number. We've already determined that that is irrational. Same thing here. Okay, I can multiply straight across. 3 times the square root of 3 is just 3 root 3. 4 times 4 is 16. But since I have that radical, since I have that irrational number, that still makes it irrational. And then 3 root 2 times 11, well, I can do, what's 3 times 11?
33.
33.
It's 33, so this is 33 times the square root of 2. But that square root isn't going anywhere. It's still irrational. So if you mix it up, if you do rational times irrational, it's always going to end up being irrational. So there we go. There we have it. Are there any differences between the rules for multiplication and then the rules for addition, or are they pretty much the same?
For irrational, wait. Um, Wait, no, there's no difference.
There is no difference. So let's go ahead and write these down as well. So it's going to look almost exactly the same, this chart, but does not want to be nice and straight. There you go. It's going to look almost exactly the same because the rules kind of go hand in hand with addition and multiplication. So this time I'm talking multiplication. So I'm going to put a multiplication symbol. Rational times irrational is always rational. When you mix them up, so irrational times rational, will it ever be rational?
No.
Nope. So it's never rational. And then irrational times irrational sometimes is rational, sometimes it's irrational, so we're just going to write sometimes rational. It's the same exact rules, same rules for addition as multiplication. I just realized this should say multiplication. My bad. Okay. So take another 30 seconds to finish writing these, and then we'll do one little practice problem, and then that'll basically be it for today. All right, is anybody still writing down? Okay. All right, so a couple questions. First one, is the product of the square root of 2 and the square root of 8 rational or irrational?
Irrational.
Irrational. Any votes for rational? Okay, so, okay, I see a couple. A couple people raise their hand. So, 2 square root of 2, irrational. Square root of 8, irrational. And we know that irrational times irrational is sometimes rational. So we got to watch out. So we got to check. So let's see. What can I do? Oops, what can I do between these two numbers since we're multiplying? Since we're multiplying, what can I do with them?
We can multiply them in the same bracket.
Yeah, they can both live under the radical. So this is the same as 2 and 8. 2 times 8 is
16.
16. And what's the square root of 16?
2. Wait, no. 3. Wait, no. I'm sorry.
What is it?
4.
4.
It's
4.
4. Yeah. So in this case, we end up with a rational answer. And so that's the big thing to take away is that you have to check because there is no rule when it comes to two irrational numbers. Sometimes it's rational, sometimes it's not. So you always have to check to see if you end up with a perfect square, because sometimes you might. So it's always a good idea to bring them under the same radical, multiply them, and just check to see if this is a perfect square. So I just wanted to quickly do that one. And then this is the last one. Oh, no, we're not going to have time for all that. You know what? Let's do these tomorrow. I'll leave these for tomorrow. So for today, that is all. And then tomorrow we'll do all these practice problems. And that'll be it for this week, y'all. It's Thursday. We're almost there. It's almost Friday. So good job on that. You've almost made it through the week. Don't forget that there is an assignment. It is one assignment due on Friday at midnight. It's already up. I saw a couple of you already did it, so good job if you did. And if you haven't, then tonight would be a good night to get it done. So I'll see you guys tomorrow. Have a nice rest of your day.
See you tomorrow, Ms. Lo.
Bye.
Green.